Hello guys, Cyprien again, and welcome in the next video of this series about OnScale Analyst 101. And in this video, we'll do together a little exercise. So it's a very good exercise to practice all what we've learned in the previous video at once. Make sure that you remember how to set up a grid and how to make a very simple geometry model. So we'll do all that in Analyst, and I'll start from scratch. Well, not exactly from scratch. I'll use the template here on the left, and I'll show you how to recreate the grid and the model here. So of course, you don't have to do that every time. You could just use any of the template models that we already seen in the previous video, or download some of the models we have already on the website. Or you could create the geometry graphically in designer mode and then generate the script out of that, and then you'll get exactly what you need. The purpose of this exercise is really to practice the basics, because knowing the basics is what make you good at it. So once you understand all these steps and you're really good at doing that, this is the foundation of becoming even better and better and understanding how it works. So let's start. Okay, I am now in OnScale Analyst mode. And the only thing I did is that I opened a new Analyst sheet like that. I pasted the template that I had on the slide previously, and I saved that into FLX INP input file. Now, what you see in green here are only comments that will help me to remember the different steps which are required to generate the geometry. The first comment here is just to tell that I want this model to use all the cores and processor available on my machine. So it's basically on the top on all the files. And the last comment, the term, will basically pose the model, because now we are looking only at the geometry parts, but of course they will be in the other videos of this series that will come after. We'll look at how to assign boundary condition, how to assign loads, and how to actually calculate and look at the results. Right now, we're still looking at making the geometry, so there will be nothing here. So I'll put the term to pose the model. That's it. Okay, so now let's follow all these steps to generate the model. So what will I need to do at each of those steps? Create variables. So here I need to create variables that will be able to model my grid. So I will use the same command to create a lot of variables, right? In this section, which will be probably the most complex one, I will have to create the key points to accurately model the dimensions. So what will come in this session is, if I remember, key chord, and then I will have to use get to get the maximum of the key chord. And then I will use key index macro to generate the nodes, and finally they will need to extract the maximum of those nodes that I will call. So this will be a variable. Okay. So I'm first, putting it like that very simply, and then I will put the real comments. Now to create the grid, I will need to use the grid command. So this will be like that. To map the physical geometry to the grid of the nodes, I will need the geom command. To read the material from file, I will use simp read and then the name of the file. To allocate the material of the grid, I will use the site command. And to plot all that, I will use graph command. So now let's go into specifics and let's do all that. So first, let's create just the simple grid, and then we'll look at how to create the PZT on top of that. So let's create a variable called xmax, which will be equal to 10 millimeter. So 10 e minus 3. And you know what? I don't like to have to write this e minus 3 every time. So what I'll do is that I'll create a variable called unit simp unit, which will be equal to this millimeter unit. And instead of writing like that, I will basically write multiply by this unit variable. So when you call a variable, you put this $sign. Don't forget to put a space in between each instruction and the multiply in the middle. So every time I write a variable, which will be in, because everything is in millimeter here, but my model should be defined in SI unit, in meter unit, so that's why I need to multiply all this by this. Okay, anyway, I have the X max of my grid. Now let's do the same and call it Y max. Okay, so my grid will be in X direction will be 14 by 10. Now I need to create the key points to go for that. So the command here is simb, and you see that once you write the real command, you still to have you start to have some indications here that will help you. So sim key chord direction X, the index begin at 1, the value will begin at 0, and the only value that I have now will be my X max value. So I will only have one key point which will be equal to the maximum of my grid. Now I need to extract the maximum index. So for that, simb get, I will save that in a variable called edx, and I use a function called root max, which is embedded into Analyst. If you want to know this function, you can right-click and go to the help, and it will tell you what it does. It basically analyzes all the key points available and extract all this and put the maximum of those key point into the variable idx. So I'm able to use this. Well, I already presented that before. So if you're not clear about this, just watch the previous video. Now let's do the same for the y. It will be y max. Then this will be j dx, and this will be root max of y. Sorry. Okay, so that's done. Now I'm using simb key index in x to extract. So into the I variable, which will be my indices for the nodes. It starts from 1 and it will finish at edx that I have extracted here into this variable, and it goes from, so this is the val index start. So this is 1, and the spacing, so this is the mesh size basically, so I don't have that yet, so I'll call that box. So I'll put a box here, box, and the minimum value will be 1, which means that I will go from one interval to one interval. And let's define here, so let's copy that. Let's define the size of my mesh. Size of my mesh will be 0, let's start with 0.5, right? 0.5 millimeter. Okay, so I have this. Let's copy that for J index. This will go 1 to JDX, and the rest is the same. Now I need to extract the maximum value of the nodes, and to do this, I am using simb. So I'm creating a new variable, and the value of this variable will be equal to I and edx. So the values located in the EDX variable will be the last, will be basically the number of the last of the key points. So if I have 5 key points, EDX will be equal to 5. So when the interpreter reads this variable, this EDX is replaced automatically by 5, and this EDX gets equal to the value saved into $I5. So that's how it works. Now let's create another variable here, which will be equal to J, and this will be J and JDX. Okay, so this part, which it was really the most difficult. So this is done. Again, you really don't have to do this. This is just because I want to show you from the start how to do this exercise. So watch it closely. Now let's create the grid. So to create the grid, just take these values. So we'll make a grid which is equal to, so the size of the grid will be equal to the last value of those key points, or nodal key points, right? And this is, so this could be a 2D model. It's no indication is really given on the slide that this should be axisymmetric, but I want to make it axisymmetric. So to do that, let's go into the grid command. Let's have a quick look at the help. And you see that you have grid, iGrid, JGrid, and you have something called constraint at the end. So constraint can be equal to, for 2D models, if I use axis y, this will be axisymmetric about y-axis. So this is the command to create axisymmetric grid. So axis, so I have to use axis y here. Okay, got it. The grid is done. Now geometry. So to create the geometry, I'm using the key points I already have. So let's have a look at those key points actually. So how can I have a look at that? Let's put a term here first. And let's run. So we don't have any visualization because I didn't print all that. But you see that in the variables here on the left, you start to see the key points. So for the moment, I have 2 key points, x1, x2, y1, y2, and I have 2 key points in nodal key points and j nodal key points. All right, so I have, those are the key points I defined up to now. Now I just have the grid, right? Basic grid. Okay, so let's stop the preview. Now that I have an idea that it seems to be working, let's create the geometry. So geometry, I'll use the command key point like that, key pnt. And here I basically have to give it the maximum value, which is this idx and gdx. So this is it for the geometry. So now I have mapped the physical geometry to the grid of nodes. Now, now the materials. So to save the material to a file, I need to have already a file in which I have saved those material data. So let's do that. Let's do it from scratch. Let's generate a new file in which, let's go to project materials. And what I want is fluid water. And I want also piezoelectric PMT3. And don't forget to change the polling to Y+. And this is done. And I don't see anything. Oh yeah. So now what I have to do is to basically save the material to the clipboard. There's a button here. So if you do that, paste it. Now you get the project material list, and I can save that to a file. So choose the right extension, prgmat, and already have one. So I'll call it, let's change the name, my mats. Okay, my mats. Now let's go back to this, and the only thing I have to do, so let's put some thing like that, and you have to put the name of my file, mymaths.prgmat. Okay, so now I'm reading those materials from the file, and I have those water and PMT3 materials available. Now let's assign, so the next step is to allocate the materials to the grid. So let's generate a region which will be water. So I only have one material for the moment. And because I didn't specify any specific region, this will be assigned to the full grid. Save that. And let's plot all this. So plot material and okay. Let's remove the term here that I put. And let's try to preview them all, hoping it works. Okay, I'm getting some problem here. Invalid constraint condition access SY. Okay, I did a small mistake here. Let's correct that. Okay, so now, okay, I get some visualization, so it's correct. Now I don't see the nodes. That's because I'm using the new, relatively new visualization. So to plot the nodes and the elements, I have to use type standard and use the option line on. And if I do that, I'm seeing the grid. So I have a grid 14 by 10 with an element size of 0.5 millimeters. So this is it. Now let's have a look again at the exercise that I want, because this was only to set up the basic template. So I could have started from that, but I just found it would be better to just show you the whole process again, so you remember what each of those commands does. Okay, let's have a look again. Okay, so this is the exercise. This is what we are trying to do. So now I have the water already. Now I need to place the PZT material in the water. So you see that I have 1, 2, and 3 variables to define. PZT rad, PZT thickness, and water size. Because water size here and here and here are the same variable. And let's look at the value. PZT rad should be 10 millimeter. PZT thickness is 2, and water size is 4. Okay, so let's start to add those new variables to represent the dimension of my PZT. Simp PZT thickness, simp PZT rad, and then I have the water simp water size. Now I said the PZT thickness would be equal to 2 millimeters, so I'm just copying that, and instead of 10 putting 2. The radius is 10, so that's good, and the water size is 4. Okay, so now that I have those 3 dimensions defined, the only thing I have to do is to modify the generation of the key points so that it generates the right points in my geometry. So I will delete this Xmax, and instead of that, I will add, so if you remember, first it's PZT rad, like that, and then it's water size, like this. And because it's a variable, don't forget to put the $sign, otherwise you'll get an error. Now let's do the same for the Y direction. So in Y direction, I had 1 water size, 1 PZT thickness, and 1 water size, right? Now, if I put a term here and I look at the key points generated, I should have more key points generated. So let's preview the model. And now you see that in X direction, I have 4 key points. In X direction, I have 3 key points, which is normal. And I can see the first key point X2 is defined at 10 millimeter, which is okay. And those are the dimension of my key points in Y direction, which is 4, 6, and 1, which corresponds to the dimension I entered here. So it means it's okay. So let's stop the preview. Let's take this term here and let's go down. And in the site allocation of the material to grid, the only thing I have to do is to add another region, which will be allocated with PMT3 material. And I want to define that in between the key points. So in X direction, it will be key point 1 and key point 2. And in J direction, it will be J2 and J3. Save that, and let's preview this, and it works. So I have defined my model in between this. And this model is parametric. So if I went to decrease the box size and put it 0.2, you see that my model is the same, and the size of the grid changes. So I'm able to refine the mesh with this. And that's it. That completes this exercise. So again, I'll put the script in the description. So the final script and the initial script. So I strongly advise you to try to go through all these steps like I did in this video. If you can't do it at the first time and you get some problems, well, look well at the code, see where are your problems, where is the difference with your code. And once you understand this kind of simple scripts, you'll see that it will be much more clear on how more complex models work. Okay, so thank you very much for watching, and I hope this was very useful for you to understand this. See you in the next videos.